Before we begin, let's look at examples of some common chemical reactions, like the burning of coal. When coal is burnt, the chemical energy stored in the molecules is released as heat or thermal energy. Another example is that of burning of fuel in a car engine. When the fuel burns in an engine, it converts the chemical energy to mechanical energy, propelling the car to move along the road. In both the examples, chemical energy, that is the energy stored in the bonds of atoms and molecules, is converted to other forms of energy. Thus, various forms of energy are interrelated, and under certain conditions, these may be transformed from one form to another. The branch of science that deals with the study of different forms of energy and the quantitative relationship between them is known as thermodynamics. The term thermodynamics is derived from the Greek word thermos, meaning heat, and dynamics, meaning flow. It was coined by James Joule in the early 19th century. Thermodynamics deals with the energy changes within a system. A system in thermodynamics refers to that part of the universe in which observations are made. For example, the tea in the teapot is a system. The part of the universe that is not a part of the system but can interact with the system is called a surrounding. In this case, the room in which the teapot is kept is the surrounding. Systems and surroundings together constitute the universe. The part that separates a system from its surrounding is known as boundary. In this case, the wall of the teapot is the boundary. Note that a boundary can be real or imaginary, and it controls the flow of energy and matter into the system or out of the system. In thermodynamics, based on the movements of matter and energy between a system and its surroundings, systems can be classified into three types. These are open system, closed system, and isolated system. Let's look at each system. A system is said to be open if it can exchange both energy and matter with its surroundings. For example, tea becomes cold when left open for some time in a container as a result of exchange of energy with the surroundings. At the same time, some amount of tea escapes from the cup as vapor. This is because of exchange of matter with the surroundings. Hence, this is an example of an open thermodynamic system. A system which permits the exchange of energy but not the exchange of matter across the boundary with its surroundings is called a closed system. For example, if tea is kept in a closed steel teapot, it takes some time to cool down. This indicates that energy is exchanged with the surroundings. However, as vapor cannot escape from the container, no exchange of matter is possible. Hence, this stands as an example for a closed thermodynamic system. A system that can exchange neither energy nor matter with its surroundings is called an isolated system. For example, the tea kept in a thermos flask remains hot and the vapor also doesn't escape out. This is because neither matter nor energy can be exchanged with the surroundings. Hence, this is an example of an isolated thermodynamic system. You have learned that a system is a part of the universe in which observations are made. In order to make these observations, it is important that we know the state of the system. By state of a system, we mean the condition of the system in terms of measurable, macroscopic properties such as temperature T, pressure P, and volume V, to name a few. The first state of the system, that is, the state before the change, is called the initial state, and the last state, that is the state after the change, is called the final state. As a change in the magnitude of these properties changes the state of a system, these properties are called state variables or state functions. In other words, properties whose values depend only upon the initial and final states of the system and are independent of the manner in which the change is brought about are called state functions. Macroscopic properties, on which the state of a system depends, are further divided into extensive properties and intensive properties. Extensive properties are properties that depend upon the quantity of the matter contained in a system. Examples of extensive properties are mass, volume, and heat capacity. For example, 200 milliliters of water takes up more volume than 100 milliliters of water. Intensive properties are properties that are independent of the amount of the substance present in the system. Some examples of intensive properties are temperature, pressure, freezing point, and boiling point. For example, boiling point is an intensive property because whatever be the quantity of water, it always boils at 100 degrees Celsius. When the state of a system changes, it implies that some thermodynamic process has occurred on the system, and energy has been either added to it or removed from it. The energy stored within a substance or a system is known as the internal energy of the system. In other words, internal energy is the sum of all the possible kinds of energy of a system. Internal energy is represented by capital U. The absolute value of internal energy cannot be found. However, change in it, represented by delta U, can be found. Internal energy U changes when work is done on or by the system. Heat passes into or out of the system. Matter enters or leaves the system. Let us discuss the change in internal energy brought out by work done on the system. Let us take a certain amount of water in a thermos flask or an insulated vessel that does not allow heat exchange with the surroundings. Such a system is called an adiabatic. The state of such a system changes without an exchange of heat, and thus the process is called an adiabatic process. In other words, delta Q is equal to 0. We can bring a change in internal energy in a system by two ways. In the first method, internal energy can be increased by doing some mechanical work. For example, by churning the water. Let UA be the initial internal energy of the system at temperature TA. After churning, internal energy changes to UB as temperature increases to TB. Thus, the change in internal energy is given by delta U is equal to UB minus UA. In the second method, internal energy can be increased by the same amount by doing electrical work. In this, an immersion rod is kept in water and the temperature before and after is measured. We find the change in temperature as Tb minus Ta. Hence, the change in internal energy, delta U, equal to Ub minus Ua. Thus, internal energy changes to the same extent either by doing mechanical work or electrical work, which indicates that it is independent of the mass.